Alrighty, so in this one we're going to be looking how to model population growth using geometric sequences. So one summer, a farmer estimates that the number of locusts swarming in a particular region is tripling each week. At the beginning of summer, authorities estimate locust numbers to be 170,000. Estimate locust numbers 5 weeks later. Now this becomes a counting problem because our first number given to us is not the first week, it is the 0th week. This is an initial value. So we haven't really talked about T0 geometric sequences. Now they look a lot like the arithmetic sequences. The same changes happen. So let's talk about them. For a T0 geometric sequence, we get T0 is equal to the first term, and then R and N and Tn, and everything is all the same. The difference is this. The equation becomes this. Tn is equal to T0 R to the N, or T0 R to the N. Okay? So there's no N minus 1 bit, and instead of T1, it's just T0. That's it. That's how you use the geometric T0 version. Once again, this is not a formula sheet one, so this is one you should probably know. So this is T0, and it says that it's tripling, so we would say that's R equal to 3. It's getting multiplied by 3 each time. And 5 weeks later, well, it depends how we set things up, but we're saying Tn is the population of locusts after n weeks. Obviously, you could call this P of W instead, but who doesn't like T of N? Let's do it. Let's do P of W instead. So P of W after W weeks. Okay? So just for something different. Okay, so let's start off with the T0. So we know T0, not T0 anymore. It's now P0 is equal to 170,000. R is equal to 3, and N is equal, not N, our count is now W, so W is equal to 5. Alrighty. So using our formula instead of this, we've got Tn equals T0 R to the N. Well, we're going to get Pn is equal to 170,000 times 3 to the N, except it's not N, it's W, because we're now using W as our counter. And we're looking for W equals 5, so P5 is equal to 170,000 times 3 to the power of 5. Now in this particular case, you can see that the population grows to 41310,000, or if you put the commas in, 41,310,000. Alrighty, so that's the population just after 5 weeks. So that's part A complete. But part B asks us to work out how many weeks it will take for the locust numbers to increase from 170,000 to over 1 billion. So it's a 1 with 9 zeros after it. So we're interested in when the population, P of W, is greater than 1 billion. 1,000,000,000,000,000. Okay, that's what we're interested in. How do we work this out? Well, it's actually not so bad. We use the old guess and check method. We already have a P of W formula, 170,000 times 3 to the power of W, and we just need to guess values of W until we get to 100 billion. So guess and check. So for my first guess, let's try, well, we know that 5 weeks isn't enough because we only get 41 billion. Let's try 8 weeks, so weeks equals 8. So this is my first guess, and we get P of 8 is equal to 170,000 times 3 to the power of 8. Alrighty, and we certainly get over 1 billion. 111,537,000. So that's actually just over 1 billion. Now, maybe I'm just very good at guessing and checking. But this doesn't improve, because just because it's bigger doesn't mean that it's the first one that's bigger. So in order to confirm, we need to try W equals 7. So P of 7 is equal to 170,000 times 3 to the 7. Alrighty, and in this case, if we put that in, yes, here we go. This is 371,790,000. Alrighty, so which is too small. Alrighty. Therefore, it will take 8 weeks for the population to grow over 1 billion. Only 8 weeks. There we go. So just as a reminder, for most of the geometric stuff, we can just substitute in, but just in case you're ever looking for the n, the power bit, which in our case was w, then you need to use the guess and check method. It's the only option, unless you want to learn logarithms. I'll see you in the next one. Goodbye.